Welcome to this concept explainer, brought to you by CBSE ScoreLab of ProfSam.com. That is ProfSam.construct. Today we are starting a deep dive into the fascinating world of Unit 4, moving charges and magnetism. We promise you a simple conceptual explanation that will make this crucial chapter much easier to understand and remember. Okay, let's unpack this with a simple observation. So, imagine you are sitting at home studying, and you have a small magnetic compass just sitting there on the table. You switch on a nearby table fan or maybe a lamp, and suddenly the compass needle just twitches. It deflects slightly. Why would that happen?
That seems so counterintuitive. I mean,
Yeah.
in our earlier units, we always treated electricity, static charges and magnetism from permanent magnets as two completely separate things.
Exactly.
So we learned that static charges have electric fields.
Mhm.
But how can a simple electric current, just the flow in a wire, suddenly move a magnetic compass? It feels like two different worlds colliding.
That collision.
Right.
That's the key to this entire unit. The simple fact that electricity in motion, a current, produces a magnetic effect is really our starting point. But let's think much bigger for a moment. Let's go. Planetary scale. Consider the stunning light show of the northern lights, the auroras.
Right. Those spectacular lights are caused by the sun, aren't they? Charged particles hitting our atmosphere.
Precisely. Those particles are constantly streaming from the sun, but they get deflected. They get trapped into the polar regions by the Earth's own gigantic magnetic field. The Earth acts like a massive bar magnet shielding all of us. Now, here's the surprising part. Where does that planetary shield even come from?
I always just assumed it was a permanent magnet. Like the Earth's core is just one big piece of magnetized iron.
That's the common assumption, but the core isn't static at all. Earth's magnetic field exists because the molten iron inside the outer core is circulating. It's churning vigorously. This circulation of charged, conducting liquid metal creates a huge internal dynamo, and that is basically moving charge on a planetary scale, a giant current.
Wow. So the very thing that keeps us safe from all that cosmic radiation, the Earth's magnetic field, it's fundamentally generated by electric current in motion inside the core.
Yes.
So that means the tiny twitching compass needle on my desk and the giant planetary shield, they're linked by the same core principle.
Precisely. That is the bridge we need to cross. So the fundamental core idea, the zero-level concept for all of Unit 4 is this. Magnetism is not a separate force. It is the electromagnetic force, just viewed from a different reference frame.
Okay, can you elaborate on that reference frame idea? That sounds a little like something from relativity, not just electricity.
It is a profound insight, actually. So imagine you have a single stationary electric charge. If you stand next to it in your reference frame, you only measure an electric field coming from it. This is basically Unit 1 and 2 electrostatics.
Okay, that's familiar.
Now, what if you start moving? Suddenly, that stationary charge appears to be moving relative to you. And what do moving charges create? They create a current. So in your new moving reference frame, you observe not just the electric field, but also a brand new magnetic field. The reality hasn't changed, only your perspective has.
So the static charge gives only an E field, but if that charge moves, it reveals the B field component of the same electromagnetic reality.
That's the key deduction. Moving charges create magnetic fields, and, well, moving charges also feel forces in those magnetic fields. Let's use an analogy to ground this idea. We can call it the traffic flow model.
Okay.
Imagine a long, straight highway is space, and the continuous flow of cars is the electric current. When traffic flows steadily, it creates a sort of invisible traffic wake or disturbance around the highway, patterns of influence that spread out perpendicular to the flow.
And that traffic wake is the magnetic field.
Oh, exactly. And the faster the traffic moves, the higher the current, the stronger the wake, or the stronger the magnetic field it generates. For a strong visual, a mental picture, imagine a copper wire with billions of electrons streaming through it.
Okay, I'm picturing it.
Picture that electron flow as a sort of blue river of charge moving straight down the wire. This invisible river creates a magnetic field that circles the wire, like concentric red ripples perpendicular to the current. That is the geometry that Ørsted discovered.
Red circles around the blue current, so the B field is circling the wire, not moving parallel to it. I can see that.
Precisely. And this insight, which unified these two forces, happened way back in 1820. The Danish physicist, Hans Christian Ørsted, he noticed during a lecture that when he switched on a current in a wire, a nearby magnetic compass needle deflected immediately.
It was an accident.
A complete accident. But it proved that moving charges or currents produced a magnetic field in the surrounding space. And that simple discovery, it's the foundation for everything that runs on electricity today. Motors, generators, everything. So now that we understand that moving charges create these fields, let's shift to the effect these fields have on other moving charges. NSERT formally defines the total force a moving charge experiences in both electric and magnetic fields. We call this the Lorentz force.
The Lorentz force, right.
Now, before we break it all down, I want you to please read the formal expression for the Lorentz force from the source material, the one that includes both components.
Okay. Reading verbatim from source 1. The total force on a charge $2 moving with velocity dollars in the presence of magnetic and electric fields $1 and $, respectively, is called the Lorentz force. It is given by the expression phi$ equals Q plus V times B.
Excellent. Now notice the two parts inside that bracket. The first part, QEEE no, is the electric force we already know from units 1 and 2. That force is parallel to the electric field. It accelerates the particle. But the magnetic part, 1 magnetic 2 times B, that's the new puzzle we have to solve.
And it looks more complex because of the cross product.
It is, and we need 5 logical steps to really understand this. This is where most students, they lose conceptual clarity. So step 1, the force requires a charge and a field. The magnetic force is proportional to the magnitude of the charge, $2, and the strength of the magnetic field, bad dollars. This is intuitive. Step 2, force requires motion. This is crucial. The force depends on velocity, $5. If a charge is stationary, so velocity is 0, the magnetic force is 0.
Wait, that's a critical point. So if I just hold an extremely strong magnet next to a static bunch of electrons, nothing happens. Magnetically, I mean.
Absolutely nothing. A magnet only exerts a magnetic force on a charge if that charge is already moving.
Yeah, I got it. Motion is a must.
Step 3. The force includes the vector cross product, $vi times B, this is the mathematical heart of it, and its geometric consequence is everything. The resulting magnetic force, $5, is always perpendicular to the velocity vector, and it's always perpendicular to the magnetic field vector $.
This perpendicularity constraint seems really important. So if the charged particle moves perfectly parallel to the magnetic field lines, meaning the angle between the dollars and dollars is 0 or 180 degrees.
The magnetic force also vanishes, right?
Absolutely correct. Because the cross product calculation involves the sign of the angle between $. If they're parallel, dollars is 0.
And the force disappears?
Vanishes. The maximum force only happens when the charge moves exactly perpendicular to the field. Now, step 4. This perpendicularity has a massive consequence for the energy of the particle. Because the force is always perpendicular to the velocity, which is the direction of displacement, the work done by the magnetic force on the particle is, well, it's 0.
0 work. That's a huge difference from the electric force. It is. The magnetic field can change the direction of motion, but it can never, ever change the speed or the kinetic energy of the charge. It is only a sideways push that curves the path.
So it's just deflecting it.
Just deflecting. It's constant curving, never accelerating in terms of speed. I hope everything is clear so far. This concept explainer is brought to you by ProfSam.com. That is ProfSam.com. Now let's quickly do one very simple calculation to quantify this sideways push. Imagine an electron, so negative charge, moving at a speed of 2 million meters per second, perpendicular to a magnetic field of 0.5 Tesla.
Okay, simple case.
The simplest. Since volatile dollars are perpendicular, the force magnitude is simply $5 QVBO, so we plug in the values. The electron charge, $1 6 times 1019 coulombs. The speed 2 times 166 meters, and the field Sealer 55T.
Okay, so let's see. 1.6 times 1019, 2 times 106 times $0.5. That gives $1 6 times 1013 newtons.
Exactly. And while that number seems tiny to us, on the atomic scale, it is an enormous force. It's enough to curve the electron's path significantly. That's why electron beams deflect in old TV screens or in mass spectrometers. That constant sideways push is everything.
That calculation really makes it concrete.
Good. Now, this entire connection Ørsted discovering current makes a B field, and Lorentz's force describing how that B field acts on other moving charges. This sets up the entire unit. Next, we'll explore exactly how this constant perpendicular force makes charges move in circles, and then we'll learn the Biot-Savart law to calculate the B field strength accurately. But before we move on, let's tackle the silent killers, the common conceptual pitfalls that rob students of marks every year.
The misconceptions.
Yes. The first one. Many students believe a stronger magnetic field, by $1, always guarantees a stronger force. They just think, more B, more F, end of story.
Wait, but that sounds logical. I definitely thought that. A stronger field should give a stronger push. No.
It sounds logical, but it's wrong because you are forgetting the direction. The force depends on QV, bis, and theta. You could have an incredibly strong magnetic field, but if the particle's velocity is perfectly parallel to that field, sin theta is zero.
And the force is zero.
It's zero. Remember this hook to anchor the idea. Perpendicular gives force, parallel gives zero. Direction is just as important as magnitude.
Okay, that makes sense.
Misconception number 2, and this is maybe the single most tested concept, students think magnetic force speeds up or slows down charges. They assume it acts like an accelerator.
But we just discussed that, didn't we? The magnetic force does zero work because it's always perpendicular to velocity.
That is the correct concept, yes, but it's easy to forget under exam pressure. You must internalize this. Magnetic forces can only deflect the path. They cannot change the speed. They cannot change the kinetic energy. If you see a question where a particle is gaining speed, an electric field must be doing the work, not a magnetic one.
Oh, right. So as speed changes, look for an E field. If only direction changes, it's the B field at work.
Exactly right. And finally, please remember that the direction of the magnetic field dollars is not the direction of the force dollars. They are mutually perpendicular. Never confuse the field with the force. To make sure you never confuse those directions again, we use the right-hand rule for $5 equals QV times B. We need a solid, mnemonic, and a gesture to lock this in.
Okay, I'm ready.
The phrase anchor, to help you remember the principle, is magnetic force, perpetual perpendicular push equals curve's path without changing speed.
Perpetual perpendicular push. I like that.
Now, for the physical gesture, hold your right hand flat like you're about to give a high five. Point your fingers in the direction of dollars, the velocity of the positive charge. Now, keeping your wrist straight, curl your fingers towards B dollar, the magnetic field direction.
So fingers are V, and then I curl towards B.
Yes. Your thumb, sticking straight out, will now point in the direction of the resulting force, $5. And remember, this is for a positive charge. If the charge is negative, like an electron, you just reverse the direction your thumb is pointing.
Fingers V, curl B, thumb F in reverse for negative. Got it.
Yeah.
I see why practicing this gesture with every single problem is non-negotiable.
Exactly. Lock it into muscle memory. Practice it until it becomes second nature. All right, to summarize this introductory deep dive, here are 3 essential exam-safe points that define the concepts we've explored today.
Okay, the key takeaways.
Point 1, moving electric charges, or currents, create magnetic fields. This reveals that magnetism isn't separate, but just one face of the electromagnetic interaction. Point 2, the magnetic force on a moving charge is given by the magnetic part of the Lorentz force, $5 equals QeV times B. And because it's a cross product, the force is always perpendicular to both velocity and the field. And point 3, since the magnetic force is perpetually perpendicular to velocity, it does zero work on the particle. It only changes the particle's path, it causes curving, but it never ever changes its speed or its kinetic energy. To get maximum marks in 12th CBSE Physics, Chemistry, and Maths, visit ProfSam.com.
That is P-R-O-F Sam, right?
Yes, ProfSam.com. Keep practicing that right-hand rule. Good luck with your preparation and keep studying hard.